Alright, so now we are now we've done some basic things in the final element method, and we've now started to build some confidence in what we are busy with. And so what I want to do is say, well, when we looking at the final element program, there's sort of multiple options for final elements. That is typically one of the first things you'll find when you start using the final element package. There's a vast array of these elements. And what I just want to explore are two types of elements that are commonly encountered. The one is what's called FI, or full integration. So you recall, full integration is when we integrate the element stiffness matrix. If that element was nice and rectangular, then the full integration is really the number of Gauss integration points that will integrate it exactly. So that is essentially what that full integration boils down to. Okay, so that is sort of the minimum number of Gauss points that will integrate a non-distorted Q4 element exactly. And what the RI element stands for, is reduced integration, is essentially an element that is the same as the same element as the normal Q4. We just use one less integration point than what the full integration is using. That's all. So for instance, if the full integration element is using a 2x2 integration rule, like a Q4 full integration is a 2x2 integration rule, will fully integrate that element, and you can go and confirm for yourself. Then essentially the Q4RI element, reduced integration element, will use a 1x1 rule. And that is essentially what that goes in. So you can imagine now for the Q8 element, fully integrated Q8 element will be a 3x3 rule. Again, feel free to go in and look at the highest order polynomials to convince yourself of that. And that a reduced integration Q8 element will be a 2x2 Gauss integration rule. Okay, so that's really what it means. But the benefit of using something like a reduced integration element is it's much faster than a fully integrated element. So people often select it for that sort of primary reason, I'd say. But what I want to just highlight is what happens if you start just doing the simplest problem we can, and we have these two element options. And again, I'm going to highlight here the importance that we always verify and make sure the answers, we know what to expect the answer should be. Okay, so we don't just blindly do modeling. Okay, so first off, if I think of the structure that we're going to be dealing with, really the simplest thing we can imagine is sort of a thin plate, 1 millimeter thickness, 4 millimeter height, 8 millimeter long, applying 100 newtons as a point load here at the edge. So we're going to apply 100 newtons at that node. That's really what you have. And then we clamping this node here, it can't move at all, and all of these ones can roll up and down. That's it. That's a nice uniaxial tension kind of problem. The simplest thing we can imagine that we could model. Okay. So if I think about this, for 100 newtons divided by an area of 4 times 1, so 4 times 1 for the thickness. So I'd expect something around in the order of 25 MPa kind of solutions, sort of stresses that I would like to see. Here I can imagine there will be a lot more chaotic stuff because it's a point load. I'm not modeling it as a nice uniform load, but I'm going to pull here locally on this element here. So there might be some stuff happening here, but what I want to show you is that when we look far, far away, we want to expect to see something close to 25 MPa. And we'll formally look at this principle here that I was talking about as St. Venant's principle. But before we do St. Venant's principle and a lot of other interesting things, I just want to make one statement, and that is just highlighting the importance of a proper verification. Okay. So if we go and we use this full integration element, I'm going to just do a magnification factor of 1 for now and run this, and I start looking at what I get out. Let me just make this also. I'll look at this one now. Okay. And I start looking at this, I see essentially not much happening with it deformed, undeformed. I can see here high local von Mises stress here, but when I start looking fairly far away here, the von Mises stress is hitting around about sort of around about the 25 MPa mark. Okay. When I look here at sigma xx, when I look at this sort of color here on this side here, essentially we're hitting that 25 MPa mark. So all of it looks fairly decent. Okay, and we don't worry too much about all of this localized kind of stresses. We can just see what's going on. Is sort of what we would expect. So we can see here the sigma y at that edge there, around that edge there is lower, and then essentially the shear is also in that edge. It's also fairly low. Okay, and this is really just what we are using here is essentially 2 by 4 elements. So we're using a total of 8 Q4 elements to model this. Okay, so this is what this 2 by 4 stands for: 2 in the height, 4 in the longer length. So I want to just run it again, but just magnify a little bit what's going on, so we can just see more or less better what's going on. Okay. Let me just run this one quickly get it out of the way, because I don't want to. Okay, so that's it. Okay, so that's essentially what you see here. When I look at that, there's still not much happening. The values will stay the same, so I'm just changing the magnification factor. This doesn't change anything about the simulation. So if we make it maybe 50, I just want to show you more or less, so we get a better idea of what the magnification factor is. What's wrong with my? Make it 100. And now I start seeing some bulging happening there. Make it maybe 500 one. And when I do make it 500, we can see essentially what's happening. But let's make it 1,000 maybe to really exaggerate now what's going on. But what you see here is essentially locally, this is sort of the deformations happening here, and essentially that's I just want to make sure this one is indeed constrained in the way that I think it is. Yeah, so that is, it just so it can roll up and down. That's perfect. But you can see there's some Poisson's contraction happening as I pull on this, so that allows for Poisson's contraction. But you see essentially this is sort of a deformed state. So we can even go more ballistic if you want to see more what's going on. This is sort of a crazy view of the deformation. It almost looks like an arrow kind of thing. Okay, but this is just to demonstrate more or less for this 8-element kind of problem. And we can really look at crazily at what's going on. I would see this kind of deformation. I just want to understand this 2 by 4 does bother me a little bit there. Pool 1, Q8, and so I need to Q4, pool 1, 2 by 4, pool 1. This looks like it's. Yeah, this is what bothered me. It looked like it was constrained in. You can see there, from just looking at this graph, I can see there's something. I would expect to see the Poisson's contraction, but I'm not seeing the Poisson's contraction there. This is what was bothering me. And I can see here that the reason for that is that this 2 by 4 pool 1 is actually clamped. The way this, so that is fine to clamp there, but I don't want to clamp the vertical of these ones as well. Okay. So I just want to have it as we set each one. So this is just a quick sanity check. See, the load is 100, thickness 1. You can see here essentially 4 height, 8 length. You can just quickly verify that things are okay. So this is. Let's go back, and let's quickly run this again. Okay, so now we'll see some. Let's make it 1,000 maybe. Now we'll see at least that Poisson's contraction beautifully. This is what I wanted to see. This Poisson's contraction coming nicely. Okay. If I now zoom in to 5,000, then I can clearly see, oh, look at that. It's pulling locally quite crazily on this element, but then far away you can see it's starting to recover some nice uniform behavior. And we'll look at that in a bit more detail when we do St. Bernard's principle forming. Okay, everything looks fine, and as we've mentioned, we see sort of stresses that we would expect to see around about 3.5 MPa mark. Okay, hunky-dory. Now all we do is we do exactly the same problem, and I just modify now essentially my element integration type from fully integrated to reduced integration. So now I'm going to use a 1-by-1 integration rule. And if I do that, so I'm going to show you more or less what we see here. This is sort of the deformed shape that I get. This is what we got with a magnification factor of 5,000. And what I'm showing you here is this is a resolution I get with a magnification factor of 1. So let's maybe make this magnification factor. So this looks really suspicious. Okay, 1e minus 6. What happens if I do that? Still crazy. 1e minus 8. I'm going to look at the stresses now. I just want to show you more or less. Apologies. So magnification factor of 1e minus 12. This is how the element looks. 1e minus 14 maybe. So that's around about there. 1e minus 13. And all I did was I modeled exactly the same problem. All I did was I really just changed the element type, and all of a sudden this is sort of the deformation. Look at this. I'm putting here, but this thing is even expanding there at the edge. And if you try to interpret this, it becomes very difficult to justify anything that's going on here. If you go down and look at the stresses, all of a sudden I show you the von Mises stress for this simple problem of just pulling on this element. Yeah, the simple problem that I'm modeling, just with a slightly different element, still Q4, just reduce integration, and now my von Mises stress is 1e, so it's essentially in this range, it's 1e to the power of 17 MPa, which is absurd. Okay, if I look at sigma xx, 1e 17 MPa. If I look at sigma yy, 1e 17 MPa. So sigma xy, 1e 17 MPa. This is crazy kind of stresses that I'm getting out, and the reason for that is, if I look at this in an underformed, like a magnification factor of 1, so this is, if I were to physically look at the structure, how the thing would deform, this is sort of the deformed state of the structure. It looks like a star. Sorry, let's get to the right one. Not here, already there, so yeah. Magnification, it looks like a star. And so that is just one thing that I just want to highlight. If we don't know what to expect as an answer, I just wanted to show you how easily I can generate different solutions that vary crazily with each other, that are non-physical using finite elements. So ones that are physical using finite elements and ones that are non-physical using finite elements. And all I did was I changed an element type. Okay, so this is really why we have to take care and always verify and know what we're doing when we do the finite element method. Okay. So this is just to show you. Now I can go and say, well, this is not the only elements that we have. We also have 8 noded planar elements. Let's look at what happens with them. So if I'm going to do the 8 noded planar elements, so I'm going to leave it at we had it here at the integration factor of 5,000. So let's make it again 5,000 here and see how that compares. So if I run this one, and I see again this sort of nice arrowhead, but again nice Poisson's contraction. So this is all hunky-dory, and when I start looking carefully what it's doing on sigma xx, I can see here we're hitting that sort of 25 MPa mark. Here again, we're in that ballpark of that 25 MPa mark. So everything looks fairly well. This is now for my fully integrated version. Okay. Now I could also say let's repeat this process and make it a 5,000 and make it reduced integration for my cured element. Okay. And then we can do that. Nothing stops us from doing that. And when I do that, I can show you essentially that this reduced integration one, that I will just show you I'm running it again. This reduced integration with the 5,000 magnification factor looks fine. If I look at the 1 magnification factor, it does not look like a star that we saw with the Q4 element. Can you see that? Everything looks fairly fine. If I look at the stresses, again here, we are hitting that sort of 25 MPa ballparks. So that's from just a sanity check, everything looks fine. If I look at the 5,000 one, it looks very similar to the solution that we got to the top. The only difference is this was now a lot quicker to do because we used reduced integration, so we could get the computational benefit out.